Discover the fascinating world behind three of America's most iconic candies: Reese's Peanut Butter Cups, Snickers, and Hershey's chocolate bars. From raw ingredients like peanuts, cocoa, and fresh milk to high-speed machinery and precision automation, explore the industrial processes that transform simple components into beloved treats enjoyed by millions around the world. This is how they're made. The process for Reese's Peanut Butter Cups begins with the sourcing of high-quality raw peanuts, which form the core of the filling. These peanuts are typically sourced from farms in the southeastern United States, particularly Georgia, Alabama, and the Carolinas, where the climate and soil are ideal for peanut cultivation. Once harvested, the peanuts undergo initial cleaning, shelling, and sorting at the agricultural level before being shipped in bulk to the Reese's production facility. Quality control teams inspect every shipment, screening for mold, aflatoxins, and other contaminants. Peanuts are often tested for size, moisture content, and oil composition to ensure batch consistency. Upon arrival at the factory, the peanuts are conveyed to large storage silos. From here, the process of transforming raw peanuts into the signature Reese's filling begins. The peanuts are first roasted in large-scale industrial roasters, long horizontal drums heated by indirect gas-fired flames. These rotating drums tumble the peanuts slowly, ensuring even roasting. Temperature and humidity are closely monitored throughout the roast cycle, typically maintained around 320 degrees Celsius for about 30 to 40 minutes, depending on the peanut variety and moisture content. Once roasted, the peanuts are quickly cooled using forced air cooling tunnels to halt further cooking. The skins are then removed using a process known as blanching. In mechanical blanches, peanuts are agitated against rough surfaces or rubber belts that strip away the thin, papery skins. A series of air jets and vibrating sieves separate the skins from the now blanched nuts. At this point, the peanuts are ready to be ground. In most candy factories, this process takes place in two distinct phases. First, a coarse grind reduces the peanuts into a crumbly paste. Then, a finer grinding process, often using high-speed colloid mills or stone rollers, produces a smoother texture. However, unlike creamy commercial peanut butters designed for spreads, Reese's peanut butter filling maintains a slightly gritty texture on purpose. This signature mouthfeel is the result of limiting the duration of the fine grind and carefully controlling moisture levels. The ground peanuts are blended with additional ingredients, including sugar, dextrose, salt, hydrogenated vegetable oils, and sometimes a small amount of molasses or corn syrup solids. This mixture is prepared in large industrial mixing tanks equipped with powerful paddle agitators that ensure even incorporation. The blending process is closely monitored for temperature, viscosity, and particle size distribution, which directly affect the final texture and handling characteristics. The resulting peanut butter filling is slightly crumbly, yet cohesive, designed to hold its shape when formed, but melt smoothly in the mouth. While the peanut butter filling is being prepared, another part of the factory is busy tempering chocolate. Reese's Peanut Butter Cups use a custom milk chocolate formulation that includes cocoa solids, cocoa butter, milk fat, sugar, lecithin, and vanillin. These ingredients are pre-blended and then passed through conching machines, large vats where granite rollers continuously knead the chocolate for hours at elevated temperatures. Conching improves texture and flavor by breaking down particles and promoting the development of complex chocolate notes. After conching, the chocolate is sent to tempering units, which precisely heat and cool the chocolate in a controlled sequence to encourage the formation of stable cocoa butter crystals. Proper tempering is critical to achieving that characteristic Reese's snap and glossy finish. The chocolate must be maintained at a working temperature of approximately 88 degrees to 90 degrees for milk chocolate, depending on the formulation. Now the production line shifts into high gear with the molding and filling of each peanut butter cup. The factory floor features a long assembly line comprising conveyor belts, servo-driven depositing heads, forming stations, and robotic arms, all synchronized with computer-controlled systems. First, paper cup liners are dispensed from reels and dropped into aluminum or plastic molds that give the peanut butter cup its distinctive ridged edge. These molds are carried forward on the conveyor to the chocolate depositing station. Here, a metered amount of tempered chocolate is deposited into each mold cavity, typically via piston-driven depositors with highly accurate flow control. The molds are then gently vibrated to level the chocolate and remove any trapped air bubbles. A specialized spinning or centrifugal molding mechanism is often used to coat the sides of each liner with chocolate, forming a thin shell that will encase the peanut butter filling. Once the bottom and sides of the shell are set, often using brief passes through cooling tunnels chilled to 40° F, the molds move to the filling station. At this point, the peanut butter mixture is slightly warmed to improve flowability and deposited into the center of the chocolate shell using a second set of depositors. The volume and placement are tightly controlled to ensure the filling does not breach the shell's perimeter, which would compromise product appearance and shelf life. The partially filled molds then travel through another cooling tunnel to partially firm up the filling before the final chocolate cap is added. At the next station, another measured deposit of tempered chocolate is layered on top to fully enclose the peanut butter. Vibratory and centrifugal actions again ensure that the top layer is smooth and fully seals the filling inside. After the top layer is applied, the molds pass through the final cooling tunnel. This tunnel, often more than 30 feet long, gradually lowers the product temperature to about 50° to 60° F, allowing the chocolate to fully crystallize and harden without cracking or bloom. At the end of the tunnel, robotic demolders invert the trays and the solidified Reese's peanut butter cups drop gently onto another conveyor belt, which carries them to the packaging line. Packaging is a critical part of the operation, both for aesthetics and product protection. Individual cups are wrapped in printed foil or plastic film using high-speed flow wrapping machines. These machines align, wrap, heat seal, and cut the packaging material in a continuous motion at speeds of hundreds of units per minute. Sensors and vision systems verify proper alignment, seal integrity, and date coding. Multiple wrapped cups are then grouped into standard pack formats, such as 2-packs, king size, or multi-packs, using pick-and-place robots that transfer the wrapped candies into cardboard sleeves or blister packs. These are then loaded into shipping cartons by automated case packers and sent through weight check stations and metal detectors for final safety assurance. Cartons are sealed, barcoded, and palletized using robotic palletizers that arrange the boxes into stable stacks ready for shipment. The finished pallets are shrink-wrapped for transport and loaded onto refrigerated trucks, if necessary, depending on the season and destination. Distribution centers receive the pallets and coordinate the movement of Reese's products to retail chains, vending machine operators, and wholesale clubs. Shelf life is generally around 6 to 9 months, and climate-controlled storage is crucial to preventing fat bloom or flavor degradation in the chocolate. Inventory is rotated using first-in, first-out logistics to ensure product freshness. Reese's peanut butter cups may seem like a simple treat, but their production involves a complex interplay of food science, automation, engineering, and quality control. Each cup reflects countless micro-adjustments made by operators, engineers, and sensors throughout the line to maintain consistency in taste, texture, and visual appeal. Whether you're biting into a miniature, a king size, or a seasonal shape, the same rigorous standards apply across every variation. The process for Snickers begins long before a single bar is formed. It starts with the procurement of raw ingredients, each of which must meet stringent quality, flavor, and food safety standards. The peanuts used in Snickers are typically sourced from large-scale growers in the United States, particularly Georgia, Texas, and Alabama, where soil composition and climate are well suited to peanut cultivation. Once harvested, the peanuts undergo shelling, drying, and initial quality control before arriving at the candy factory in bulk loads. At the receiving dock, they're sampled and inspected for size uniformity, absence of mold or aflatoxins, and overall freshness. The peanuts are then conveyed to roasting units, large, gas-fired, rotary drum roasters that tumble and cook the nuts evenly. Roasting time and temperature are carefully controlled, often in the range of 300° to 330°, to ensure the development of the characteristic deep nutty flavor and golden color. As the peanuts cool on vibratory trays with forced air, their skins are loosened and removed through mechanical blanching, which typically involves abrasion and suction systems. Once the peanuts are blanched, they are screened again for foreign matter or off-grade pieces before being held in stainless steel hoppers, ready for integration into the bar. While the peanuts are being prepared, another production stream begins with the making of the nougat layer, the foundational component of every Snickers bar. Nougat is a whipped mixture, typically composed of sugar, corn syrup, egg whites, and milk powder. The sugar and corn syrup are first combined in massive stainless steel cooking kettles, where they are heated to a precise temperature, usually around 240 degF to 250 degF, to achieve the correct sugar structure and viscosity. This hot syrup is then transferred to continuous mixing tanks, where it is combined with whipped egg whites and other dry ingredients. The blending process is highly aerated, giving the nougat its light, spongy texture. The finished nougat is deposited onto a moving conveyor belt lined with parchment or plastic film. It spreads out in a continuous sheet, generally about 1 to 2 inches thick. A series of levelers and rollers ensures uniform height and density across the sheet, which is then cooled slightly as it travels down the line. Once cooled and set, the nougat sheet proceeds to the caramel layering station. Caramel production occurs in its own dedicated section of the plant. A blend of glucose syrup, sucrose, dairy cream, and butter is cooked in open-jacketed kettles or vacuum cookers, where it is continuously stirred to avoid burning and to control the Maillard browning reactions that give caramel its signature flavor. The exact temperature and cooking duration are tightly monitored, typically between 240 degrees Celsius and 260 degrees. As soon as the desired consistency is achieved, firm enough to hold its shape but pliable enough to slice, it is poured or extruded onto the moving nougat sheet. The hot caramel forms a second, cohesive layer atop the nougat. To ensure perfect adhesion and uniform thickness, the bar sheet passes under heated rollers and through spreading nozzles that guide and adjust the caramel's distribution. The line is equipped with infrared sensors and weight check systems that continually monitor thickness and material ratios. Once the caramel has slightly cooled and stabilized, the bar sheet moves toward the peanut application zone. Roasted peanuts are sprinkled onto the warm caramel layer in a controlled shower using vibrating feed trays and metered dispensers. The combination of slightly sticky caramel and downward pressure ensures that most peanuts adhere securely. Excess or misaligned nuts are brushed away by rotating silicone paddles and collected for reuse or reprocessing. The peanuts used here are not only flavor critical, but also provide a distinctive crunch and texture contrast to the softer nougat and caramel. With all three internal layers assembled, nougat, caramel, and peanuts, the composite sheet now travels to the cutting area. Here, guillotine-style knives or rotary blade systems cut the long sheet into bar-length strips, typically around 1 inch wide. These strips are then cross-cut into individual bars, using synchronized high-speed blades. Every bar is now a complete unit, except for the chocolate coating. Before coating, the uncoated bars, often referred to as centers, pass through a quick chilling tunnel to firm up the layers and maintain bar integrity during enrobing. Once firm, the centers are deposited onto a wide enrobing belt that passes through a chocolate waterfall. This enrobing process involves a curtain of tempered milk chocolate cascading down over the moving bars. As the bars move through the curtain, chocolate coats the top and sides. A bottoming plate or chocolate pool beneath the bars coats the underside as well. The chocolate used in Snickers bars is a proprietary blend of milk chocolate ingredients, cocoa butter, cocoa liquor, sugar, milk solids, and emulsifiers. The chocolate is pre-tempered in dedicated machines that heat and cool it through specific curves to ensure stable crystal formation. This tempering is what gives Snickers its glossy finish and prevents fat bloom during storage. The temperature of the chocolate is carefully maintained between 86 degrees Celsius and 90 degrees Celsius throughout the enrobing line. As the chocolate-coated bars exit the enrober, they pass under air jets and vibrating rods known as air knives and vibrators that remove excess chocolate, improve coating uniformity, and give each bar its final shape. The still warm chocolate is soft and easily deformed, so the bars immediately enter a cooling tunnel, which gradually reduces their temperature to around 50 degrees Celsius in a staged fashion. This gradual cooling prevents cracking and ensures that the chocolate shell sets with the correct texture. Once fully cooled, the bars emerge, ready for wrapping. A high-speed automated packaging line awaits, where each bar is individually wrapped using roll-fed film wrappers. These machines synchronize bar movement with film feeding, folding, sealing, and cutting, all in one continuous operation. Heat sealers close the film edges with precision, while inline printers apply best buy dates, lot numbers, and traceability codes. The wrapped bars are then conveyed to a grouping station. Depending on the market, Snickers bars may be packed individually, bundled in twin packs, or combined into multi-unit boxes. Robotic arms sort and orient the wrapped bars, placing them into cartons that are then sealed with hot melt adhesive. The packed cartons are passed through metal detectors and weight verifiers as a final check before palletization. Palletizing robots load the boxes onto standardized pallets, wrapping them tightly in plastic film for protection and stability during shipping. From there, pallets are staged in climate-controlled distribution centers. Temperature and humidity must be carefully controlled, especially in warm climates, to preserve the bar's texture and chocolate integrity. Snickers bars are then distributed to retailers, wholesalers, and vending machine operators worldwide. Shelf life for a standard Snickers bar is generally between 9 and 12 months, assuming proper storage. Mars maintains rigorous quality control protocols, including sampling every batch for flavor consistency, structural integrity, and microbiological safety. Automated inspection systems use vision technology to detect misaligned bars, incomplete coatings, or wrapper defects, automatically removing flawed units from the line. Throughout the plant, hygiene is paramount, with clean-in-place systems for all equipment and strict allergen controls to ensure product safety. What makes Snickers particularly remarkable is how such a complex, multi-layered treat can be produced with such uniformity at an industrial scale. From raw peanuts and liquid caramel to perfectly wrapped bars stacked on pallets, every aspect of production is optimized for speed, precision, and global distribution. Millions of Snickers bars roll off the line each day, each one representing a perfected system of mass food manufacturing. It all begins with cocoa beans for Hershey's chocolate, which are the fundamental raw ingredient in all chocolate. Hershey sources its cocoa beans primarily from West Africa, countries like Côte d'Ivoire and Ghana, where the climate, soil, and traditional farming practices produce high-yield crops with desirable flavor characteristics. Once harvested, the cocoa beans are fermented in banana leaf-lined piles and dried under the sun before being packed in jute bags and shipped across the ocean to Hershey's production facilities in the United States. Upon arrival, the beans are subject to rigorous testing. Random samples from each shipment are roasted and analyzed for aroma, acidity, moisture content, and potential contaminants. Approved beans are stored in large silos, sorted by origin and quality grade. From here, the first major step in the chocolate making process begins roasting. Roasting is not just about cooking the beans, it's a chemical transformation that unlocks the complex flavors hidden within the cocoa nibs. The beans are fed into large, rotating drum roasters or continuous belt roasters and exposed to carefully controlled dry heat at temperatures between 250 degrees and 300 degrees for 20 to 30 minutes. This Maillard reaction develops the chocolate flavor while drying the beans further and loosening the outer shells. The duration and temperature of the roast are adjusted depending on the origin and size of the beans, with constant airflow and humidity control. After roasting, the beans are cooled and sent through cracking machines that break them open, separating the brittle outer shells from the inner nibs. The broken shell pieces are removed through winnowing, a process that uses airflow to lift away the lighter shells, leaving behind clean cocoa nibs. These nibs are the essence of chocolate, rich in cocoa solids and cocoa butter. The nibs are then ground into a thick, gritty paste called chocolate liquor, not to be confused with alcohol. This step is performed in heavy-duty grinding mills, such as stone refiners or steel disc mills, which apply intense pressure and friction. As the nibs break down, their fat melts, turning the mass into a thick, flowing fluid. At this point, the chocolate liquor is still unrefined, with a coarse texture and bitter flavor. For milk chocolate, Hershey adds a blend of sugar, milk ingredients, and sometimes vanilla and lecithin to the chocolate liquor. One of the defining features of Hershey's milk chocolate is its use of fresh fluid milk that is processed in-house. Unlike European chocolates that often use powdered or condensed milk, Hershey pioneered a method of processing fresh milk into milk crumb, a dehydrated mixture of milk solids and sugar, using vacuum cooking and drum drying techniques. This milk crumb, with its slightly tangy cooked flavor, contributes to the uniquely Hershey taste. The chocolate liquor, milk crumb, and sugar are blended in large stainless steel mixing tanks, forming a uniform paste. At this stage, the mixture is still coarse and gritty, unsuitable for final chocolate texture. It must be refined. The refining process involves passing the chocolate mass through a series of roller mills, typically 5-roll refiners that reduce the particle size of the solids to less than 30 microns. The goal is to achieve a silky smooth mouthfeel without any noticeable graininess. Once refined, the chocolate enters the conching phase, one of the most critical steps in flavor development. Conching is a process of continuous mixing, aerating, and heating the chocolate over many hours to improve its taste and texture. Hershey's uses a combination of traditional longitudinal conches and modern rotary conches that knead the chocolate at controlled temperatures, typically between 120 degF and 180 degF. This process helps evaporate undesirable volatile acids, mellow bitter notes, and fully integrate the milk and cocoa flavors. The viscosity and aroma are fine-tuned during this stage through mechanical shearing and time adjustments. Following conching, the chocolate undergoes tempering, a heat treatment process that ensures the final product has a smooth, glossy finish and a crisp snap when broken. Cocoa butter can crystallize in several forms, but only one, known as Form 5, gives chocolate its ideal physical properties. Tempering involves heating the chocolate to about 115 degrees, then cooling it down to around 80 degrees, and finally reheating it slightly to about 88 degrees to promote the formation of stable crystals. This carefully controlled cycle is performed in continuous tempering machines, which maintain consistent temperatures and flow rates. Tempered chocolate is now ready for molding. Hershey's uses high-speed molding lines where liquid chocolate is deposited into polycarbonate molds in precise weights. The molds are vibrated to remove air bubbles and ensure even distribution. For classic bars like the Hershey's Milk Chocolate Bar, the molds are designed with the familiar rectangular break-apart sections embossed with the Hershey name. Once filled, the molds travel through long refrigerated cooling tunnels where the chocolate solidifies into its final form. As the bars cool, they are monitored by temperature sensors and mechanical feelers to ensure proper release. When fully set, the bars are automatically ejected from the molds and conveyed to the wrapping station. Modern wrapping equipment is synchronized with bar output and uses roll-fed film that is printed with the Hershey's branding, ingredients, and expiration codes. Wrappers are folded and sealed using rotary crimpers, and a barcode is applied for tracking. Wrapped bars are then grouped into cartons or display trays using robotic pick-and-place systems and conveyed to the end-of-line packaging area. Here, cases are formed, filled, and sealed before being palletized by automated arms. Each pallet is shrink-wrapped and scanned into inventory, ready for transport to distribution centers across the country and around the world. Throughout the entire process, quality control is a constant presence. Samples are pulled from every batch for testing. Sensory panels evaluate flavor and aroma, while lab technicians measure moisture content, fat percentage, and microbial levels. Machine vision systems inspect each bar for dimensional accuracy and surface defects. Metal detectors and X-ray machines scan for foreign objects, while thermal imaging cameras check for temperature compliance at various stages. Behind the scenes, Hershey's factories are tightly integrated with computerized control systems that track every ingredient, process parameter, and output metric in real time. From ingredient blending to chocolate tempering and bar wrapping, programmable logic controllers and supervisory control and data acquisition systems coordinate the hundreds of motors, valves, conveyors, and sensors that make up the line. These systems not only maximize efficiency and reduce downtime, but also ensure that each bar tastes the same as the one before it. Once packaged and palletized, Hershey's bars enter the post-production logistics chain. Distribution centers maintain climate-controlled storage to preserve chocolate integrity. Trucks are loaded according to first-in, first-out scheduling, and GPS tracking systems ensure timely delivery to retailers, vending machine operators, and wholesalers. Chocolate bars are especially sensitive to heat and humidity, so strict environmental controls are observed throughout transportation and warehousing to prevent melting or bloom. Interestingly, the Hershey flavor that many Americans recognize and even associate with nostalgia is not accidental. It's the result of deliberate formulation choices, particularly in how milk is treated during production. Some analysts believe the signature, slightly sour or tangy flavor found in Hershey's milk chocolate comes from the breakdown of milk fats into butyric acid during controlled lipolysis, an effect that differentiates Hershey's from creamier European chocolates. This flavor profile has become a cultural benchmark in the United States, deeply woven into American food identity. Despite decades of innovation and scaling up, the heart of Hershey's chocolate production still echoes the vision of its founder: to make high-quality milk chocolate affordable and accessible to everyone. With more than a century of history and tens of millions of bars produced annually, Hershey's remains a pioneer in automated food manufacturing, exemplifying the blend of tradition, precision engineering, and industrial food science. From bean to bar, the production of Hershey's chocolate is a story of transformation, driven by technology, but grounded in flavor. The production of a Mars bar begins with the formulation and creation of its first major internal layer, the nougat. This nougat isn't the brittle kind you might find in traditional nut candies. Rather, it's a whipped, creamy, slightly chewy foundation that gives Mars bars their signature texture. Creating this nougat at industrial scale is a carefully engineered process that blends confectionery science with mass production machinery and strict environmental controls. Before the first batch of nougat is made, however, the ingredients themselves must be prepared and stored according to strict protocols. The base ingredients for the nougat are sugar, glucose syrup, water, fat typically palm or shea oil, dried milk powder, cocoa powder, and whipped egg white or egg albumin. All these materials arrive at the Mars manufacturing facility in bulk, delivered in tankers, tote bags, or sealed sacks. Each delivery is logged, barcoded, and entered into the site's inventory system. But before any ingredient enters production, it must pass Mars' internal quality standards. All dry ingredients, such as sugar and milk powder, are transferred into enclosed silo systems using pneumatic conveyors. These silos are climate-controlled and fitted with HEPA filtration to prevent contamination from dust or ambient air. Each ingredient batch is tagged with a barcode that traces it back to its supplier, production date, and previous storage conditions. For example, sugar may be tested for grain size, purity, and color using laser granulometry and ICUMSA color unit analysis. If it's outside tolerance, it's rejected immediately. Liquid ingredients like glucose syrup and oils are offloaded into jacketed stainless steel storage tanks through filtered, food-grade hoses. These tanks maintain the ingredients at set temperatures to ensure proper viscosity for pumping during production. Glucose syrup, for instance, is kept at around 40 degrees Celsius to remain fluid enough to move through piping without crystallizing. Oils are similarly heated and agitated to prevent separation or solidification. Once all components have been approved and staged, the first step in actual nougat production begins in a dedicated mixing chamber. This space is sealed off from other parts of the factory and maintained at specific humidity and temperature levels to preserve the quality and structure of the aerated product. Airborne particles are filtered through a multi-stage air filtration system, and stainless steel surfaces are sanitized before each production run. Nougat is made in large capacity continuous mixers, automated machines that blend ingredients while precisely managing flow rate, temperature, and mixing speed. In a traditional batch process, workers would mix sugar and glucose syrup with water and cook it to a specific temperature. But in Mars's high-speed factories, this process is carried out on a continuous flow basis, meaning raw ingredients are metered into the cooking system in real time, mixed, cooked, and then aerated in a constant stream. First, sugar, glucose syrup, and water are combined in a jacketed mixing vessel and brought up to temperature using indirect steam heating. The mixture must reach roughly 115 to 120 degrees Celsius, hot enough to dissolve all solids and achieve the correct consistency for whipping, but not so hot that caramelization occurs. Inline refractometers monitor the brix level, sugar concentration, constantly, sending digital signals to a control system that adjusts syrup feed rate or cooking temperature as needed to stay within spec. Once the syrup reaches target temperature and concentration, it's transferred to a cooling chamber, where it's rapidly brought down to around 70 to 80 degrees Celsius using chilled water jackets. This temperature reduction is critical. It stabilizes the syrup mixture and prepares it for aeration with egg whites or albumin, which cannot be added while the base is too hot without denaturing the proteins. Now comes the aeration stage, where the characteristic lightness and chew of the nougat is created. A pre-prepared egg albumin solution is metered into the cooled sugar syrup in a continuous aerator. This machine functions much like a planetary mixer, but at vastly greater speed and scale. Blades spin at extremely high RPMs inside a sealed chamber, while air is injected under pressure. The result is a fluffy, stable foam that has the volume and consistency of whipped marshmallow. The air injected into the aerator is sterile and dry, supplied by an inline compressed air system equipped with microbial filters and dehumidifiers. Pressure, temperature, and air-to-liquid ratio are all controlled automatically via programmable logic controllers, PLCs, which adjust mixing speed and flow rate to maintain uniform aeration. If the density of the nougat mixture falls outside of target specifications, measured by inline densitometers, the system automatically corrects the air or syrup flow or alerts operators to intervene. At this point, cocoa powder and dried milk are added to the base. These ingredients give Mars bar nougat its unique color and rich malted taste. They are added using powder feeders that continuously meter the dry materials into the aerated mass as it exits the mixer. This blending occurs in a sealed paddle mixer with gentle, controlled agitation to avoid collapsing the foam structure. The resulting mixture is a warm, chocolatey nougat paste with a light, stable structure and a semi-elastic texture. Now that the nougat base is formed, it must be shaped and cooled. The nougat flows out of the mixer onto a stainless steel conveyor belt, forming a continuous slab about 2 to 3 centimeters thick. This slab passes through a chilling tunnel, where it is gradually cooled from around 60 degrees Celsius to just below ambient temperature. The tunnel uses recirculated cold air, zoned in multiple sections, to cool the nougat evenly without inducing condensation or hardening the outer surface too quickly. As the slab exits the chilling tunnel, it enters a cutting station. Rotary guillotine knives, synchronized with the belt speed, slice the slab crosswise into narrow ribbons, each of which will become the base layer of a Mars bar. These ribbons are then cut lengthwise by inline blades or ultrasonic cutters, creating rectangular nougat centers of uniform size. Every bar section is scanned by vision systems to check for dimensional consistency, length, width, and height, with auto-reject mechanisms removing any pieces that fall outside tolerance. The formed nougat segments are now ready to receive their second major component, the caramel layer. But before caramel is deposited, the nougat sections are spaced and aligned using lane diverters and product guides, ensuring that each bar proceeds uniformly through the next phase of production. The segments then pass into a buffer zone where their temperature is stabilized to prepare for caramel application. Now that the nougat segments are cooled, cut to precise dimensions, and cued in alignment on the conveyor system, the next phase in the Mars chocolate bar manufacturing process begins: the production and deposition of the caramel layer. This caramel is not a generic topping, it's one of the signature components that defines the textural and flavor contrast of a Mars bar. Creating this layer at scale requires a specialized process that integrates continuous cooking, emulsification, temperature control, and precision depositing, all engineered to work seamlessly within the speed and flow of a high-volume confectionery production line. The caramel used in Mars bars is made from a carefully balanced combination of sugar, glucose syrup, sweetened condensed milk or milk solids, and a specific blend of fats and emulsifiers. It's cooked to achieve a particular consistency, not too firm, not too runny, with a creamy chew that holds its shape during wrapping and storage, yet yields easily when bitten into. The production of caramel begins in a dedicated cooking area, separate from the nougat line, but synchronized with it to maintain constant throughput. All ingredients are stored in bulk near the cooking zone. Sugar and milk powders are gravity-fed from silos into high-shear premixes, while glucose syrup and fat are pumped in from temperature-controlled tanks. The emulsifiers, such as mono and diglycerides, are introduced through metering pumps in very small, tightly controlled amounts to help ensure smooth texture and fat-water dispersion. A water phase may also be introduced at the start to aid in initial dissolution and prevent localized overheating. The entire mixture is first blended in a jacketed stainless steel preheating tank, where it's brought to a uniform temperature of around 70 to 80 degrees Celsius. This pre-cooking stage ensures that all ingredients are fully homogenized before entering the main caramel cooker. From here, the caramel mix is pumped continuously into a vacuum caramel cooker, a specialized machine that allows rapid, even heating while removing excess water to control the final solid's content and viscosity. Vacuum caramel cookers work by reducing the internal pressure in the cooking chamber so that water boils off at a lower temperature. This is crucial to avoid burning the sugars or overcooking the milk solids, which could lead to bitter notes or textural instability. Inside the cooker, the mix is heated to between 115 degrees Celsius and 120 degrees Celsius. The target is to achieve a final water content of around 6 to 8%, with a sugar concentration of roughly 80 to 85 brix. Inline refractometers monitor this constantly, and the cooker adjusts residence time or heating level as needed to meet the spec. Once cooked, the caramel exits the cooker as a thick, glossy liquid with a rich golden brown hue. But before it can be applied to the nougat, it must be slightly cooled and tempered to a very specific range, typically between 45 degrees Celsius and 55 degrees Celsius. This cooling step stabilizes the caramel structure, allowing it to flow evenly during deposition without dripping or bleeding into the nougat layer. Cooling is performed in a jacketed holding tank equipped with slow-speed agitators that prevent crusting and keep the mixture homogeneous. With the caramel at the correct temperature, it's piped toward the depositing station. Here, the aligned nougat segments are conveyed under a continuous curtain-style depositor or a series of timed nozzles. Each piece receives a uniform layer of caramel, typically around 5 to 6 millimeters thick, depending on the final product specification. The depositor is precisely synchronized with the line speed, often using servo motors and optical sensors, so that each caramel stream lands squarely on the nougat block without overflow or excess. In higher speed lines, a pre-formed caramel sheet may be used instead. In this method, caramel is spread onto a separate cooling belt, allowed to set into a thin slab, and then laminated onto the nougat in one continuous motion using compression rollers. This technique allows better layer thickness control at very high production speeds and ensures cleaner edges for slicing. Once the caramel is applied, the dual layer bar now enters another cooling tunnel, usually a multi-zone refrigerated belt system that brings the caramel from 50 degrees Celsius down to just under 20 degrees Celsius. This cooling step must be gradual and controlled. Too rapid, and the caramel may contract unevenly, leading to separation from the nougat. Too slow, and it may remain sticky, interfering with the next step. Chocolate enrobing. During cooling, the layered bar is gently compressed by a roller to ensure adhesion between nougat and caramel. Then, it's passed through edge trimmers, which shave off the sides of the slab to produce perfectly square bars with clean, vertical sides. These trimmed edges are not wasted. They are collected via vacuum conveyors and reprocessed, either remelted or reformed, depending on factory protocol. The bar, now comprised of a cooled nougat base and a bonded caramel layer, is next cut into individual pieces using high-speed guillotine cutters. These are precision machines equipped with hardened stainless steel blades or ultrasonic cutting systems that minimize drag and preserve edge integrity. Each piece is exactly the length and width of a finished Mars bar, around 10 centimeters long and weighing roughly 51 to 57 grams, depending on the market. As the bars are cut, they are spaced out evenly using puck conveyors or lane dividers, aligning them perfectly for entry into the chocolate enrobing section. The temperature, moisture, and dimensional uniformity of each bar are verified by inline sensors and vision systems. Bars that are cracked, too short, or unevenly shaped are automatically diverted off the line for manual inspection or rework. At this stage, we transition into the enrobing process, the iconic step where each bar is coated in a smooth layer of Mars proprietary milk chocolate blend. This chocolate is stored in large tempering tanks, located just prior to the enrober. These tanks keep the chocolate at the ideal crystallization state, ensuring a glossy finish and firm snap after cooling. The chocolate used in Mars bars is a blend of cocoa liquor, cocoa butter, sugar, and milk solids, with added emulsifiers like soy lecithin to enhance flow properties. The tempered chocolate is pumped into the enrober, which is essentially a tunnel lined with a bottoming section to coat the base of each bar, and a curtain section to drape chocolate over the top and sides. Each Mars bar passes first over a shallow pool of chocolate to coat its underside, then directly beneath a flowing curtain that envelops the rest of the bar. A gentle stream of warm air is directed across the top to remove excess and create a rippled surface texture, a distinctive feature of the Mars bar. After enrobing, the bars are conveyed into the cooling tunnel, an extended refrigerated belt system approximately 20 to 30 meters in length. Inside, the environment is segmented into zones that gradually lower the temperature of the bars from around 32 degrees Celsius to 10 degrees Celsius. This staged cooling helps the cocoa butter in the chocolate crystallize properly, locking in the sheen and texture while avoiding fat bloom or streaks. Throughout this tunnel, air humidity is tightly controlled, generally under 50%, to prevent condensation on the chocolate. Dew point sensors and fans work in tandem with the refrigeration units to maintain a stable microclimate. The bars spend 5 to 8 minutes in this tunnel before emerging with fully set coatings, ready for packaging. As the cooled and finished bars exit the tunnel, they're fed into accumulation conveyors and grouped for wrapping. Each bar passes through a flow wrapping machine where printed film is unwound, formed into a sleeve, and sealed around the product. The wrapper is then crimp sealed on both ends and trimmed. These wrapping machines can process hundreds of bars per minute, and each wrapped bar is weighed and scanned before being discharged onto final packing belts. At this point, the product is visually indistinguishable from the Mars bar found on store shelves, but the process is still not finished. The next stage involves secondary packaging, grouping bars into boxes, cartons, and shipping trays, and preparing them for distribution. As the fully formed, enrobed, and cooled Mars bars make their way off the production line, they enter the final stages of the factory process, beginning with high-speed wrapping and continuing through automated boxing, palletization, storage, and outbound logistics. These downstream systems are critical not just for protection and presentation of the product, but also for ensuring traceability, quality retention, and supply chain synchronization. While the visible production, the mixing, cooking, cutting, and coating is complete, the final packaging and handling stages are no less intricate, built on robotics, data systems, and industrial automation designed to manage millions of units every day. The first stop is the wrapping station. Here, each Mars bar moves along the conveyor belt in single file toward the flow wrapping machine. This machine feeds a continuous roll of printed film into a series of folding arms and sealing jaws. As each bar enters, the film wraps around it in a tight, tubular sleeve, and heated crimp jaws at either end form the back seal and the end seals simultaneously. The temperature of these jaws is maintained within a few degrees of the sealing material's activation point to ensure strong, clean closures without melting or burning the film. Mars uses multi-layered packaging films that are designed not only to provide barrier protection against oxygen and moisture, but also to deliver the tactile feel and gloss that customers expect from premium chocolate packaging. The inner layer is typically a heat-sealable polymer. The middle layer may include aluminum or metallized PET for barrier properties. And the outer layer is printed with brand artwork and product information. The printed designs are registered with high-precision sensors, so every bar's logo aligns perfectly. Any misregistered wrapper is automatically detected and rejected by an optical scanner system. Once sealed, the wrapped bar passes over a check weigher, an in-motion scale that ensures the final packaged weight is within tolerance. If a bar is over or underweight, even by a gram, it's automatically diverted. Next, each unit is passed under a metal detector, which checks for any possible foreign objects that could have entered the bar during earlier processing stages. These systems are highly sensitive and calibrated daily with test pieces. Some plants also employ X-ray machines that detect not just metal, but dense, non-metallic contaminants, such as glass or stone. Bars that pass all inspections continue down the conveyor toward the cartoning line. Depending on the intended retail format, bars may be grouped into multi-packs, retail-ready trays, or shipping cartons. Robotic arms, or high-speed diverters, organize the flow of individual bars into stacks, 4, 6, 10, or 12 bars wide, and gently push them into pre-folded cardboard sleeves or boxes. These secondary packages are then sealed using hot melt glue or tuck-in flaps, depending on market requirements. Each package receives a printed label with batch number, timestamp, factory ID, and possibly a QR code for inventory tracking. From here, boxed products are routed to the palletizing station. Robotic palletizers pick up full cases using vacuum grippers or mechanical arms and stack them on wooden or plastic pallets in precise formations. Each layer is arranged to optimize space, balance, and load stability. Between layers, some systems add cardboard slips or corner protectors for reinforcement. Once the pallet reaches its programmed height, typically 1.6 to 1.8 meters, it's wrapped in stretch film by an automatic wrapper, which rotates the pallet while dispensing the film under tension to secure the load. The wrapped pallets are then fitted with pallet labels that include the SKU, total unit count, gross weight, destination code, and a unique identifier that ties back to the factory's internal tracking system. These labels are printed by thermal printers and verified by barcode scanners before the pallets are cleared to enter the finished goods warehouse. Before we go further, it's important to recognize the role of Mars factory control systems in managing this entire post-production phase. All equipment is integrated into a centralized manufacturing execution system, MES, that tracks every product in real time. Each bar, box, and pallet carries data embedded in barcodes or RFID tags about when it was made, on which line, using which ingredients, and under what conditions. This traceability is a cornerstone of food safety compliance and internal quality assurance. The finished goods warehouse is where the newly palletized bars await shipment. This warehouse is fully climate controlled to maintain optimal temperature and humidity for chocolate storage. Temperature is held at 18 to 20 degrees Celsius with relative humidity below 55% to prevent bloom, melting, or texture changes. Air circulation systems keep temperature consistent throughout the space, while insulation and vapor barriers prevent external fluctuations from impacting internal conditions. Inventory in the warehouse is managed using automated guided vehicles, AGVs, or forklifts equipped with real-time location systems. When pallets are stored, they're scanned into the warehouse management system and placed according to distribution priority. High turnover products are stored closer to the shipping bays, while seasonal or export variants may be stored deeper in the racking system. The storage time for any batch is typically less than a week, as Mars factories operate on just-in-time logistics, pushing product out daily to meet distributor orders. When shipments are requested, the warehouse team receives a digital pick list. AGVs or operators retrieve the designated pallets, verify them via handheld scanners, and stage them at the outbound docks. Before loading, each shipment is inspected to ensure it matches the order specification, is within temperature tolerance, and has intact pallet wrapping. Refrigerated or climate-controlled trucks are often used for long-distance shipments or deliveries to regions with high ambient temperatures. Loading is done using dock levelers and roller systems to ensure smooth movement and prevent tipping. During transit, temperature loggers accompany the shipments, recording data at set intervals. These loggers are checked upon delivery, and if any deviation from the acceptable range is detected, the shipment may be flagged for inspection or rejection. Mars also monitors customer feedback, market audits, and in-store quality surveys. Samples of each production lot are retained in climate-controlled storage at the factory for shelf life testing. These retained samples are periodically tested for appearance, taste, texture, and microbiological stability over the course of months, ensuring that every production protocol performs as expected long after the product has left the plant. Parallel to all of this is a dedicated quality control laboratory. Here, daily production samples are subjected to physical and chemical analysis. Moisture content, fat content, sugar crystallinity, pH, and emulsion stability are checked using instruments like Carl Fisher titrators, differential scanning calorimeters, and viscometers. Sensory panels trained in Mars' specific flavor and texture profiles evaluate samples for aroma, mouthfeel, and aftertaste. Auditors regularly conduct surprise inspections, testing product against regulatory standards in every region the factory exports to. Some facilities even run accelerated aging chambers, simulating 6 months of shelf life in a few weeks using controlled temperature and humidity cycling. This allows the company to predict how new packaging or ingredient changes may impact long-term stability before releasing them to the market. Within the final layers of Mars' chocolate bar manufacturing process lies an often unseen yet deeply critical infrastructure dedicated to innovation, iteration, and global standardization. While the production lines are optimized for high-speed consistency, behind the scenes, the company operates pilot plants and R&D laboratories, where new formulations, production methods, and equipment calibrations are continuously tested, refined, and validated before they're deployed across global facilities. Every Mars chocolate bar, regardless of where it is produced, in the United States, the United Kingdom, or other licensed manufacturing hubs must adhere to an extremely narrow window of variation. This means the bars must look, taste, feel, and behave identically, despite being produced in plants thousands of kilometers apart. Achieving this demands extensive process documentation, real-time data comparison, and coordinated updates to recipes and equipment settings across all sites. Pilot plants, often located adjacent to main production facilities, house miniature versions of the full-scale equipment, scaled-down mixers, depositors, tempering tanks, and enrobers, used not just for prototyping new flavors or bar formats, but also for stress testing ingredient substitutions, adjusting for new cocoa sources, or modifying emulsifier levels in response to regional ingredient availability or regulation. A new Mars bar variant, such as one with an added layer of cookie or a salted caramel flavor, may go through dozens of test batches before scaling. Each trial is evaluated not just for consumer preference, but for how it performs on actual equipment. Does the caramel spread at the correct rate on moving belts? Does it maintain form through the cooling tunnel? Does the chocolate enrobe correctly without altering crystallization time? These questions are answered with data from test runs that are digitally logged and used to generate predictive models before any large-scale production begins. Digital twins, virtual simulations of real production environments, are increasingly being used in these trials. These tools model fluid dynamics, thermal behavior, and mechanical stress on ingredients during cooking, cooling, and transport. They allow engineers to simulate a dozen line changes without touching a single piece of physical equipment, drastically accelerating the pace of safe innovation. Once a new process is approved, Mars Global Standardization Team prepares comprehensive change packs, which include updated process parameters, safety protocols, ingredient specs, equipment calibration charts, and software updates. These packs are then distributed to all regional manufacturing hubs, often followed by remote training sessions or on-site visits to ensure implementation is seamless. This global coordination ensures that whether you open a Mars bar in Chicago, Sydney, or Madrid, the experience is identical, down to the snap of the chocolate, the elasticity of the caramel, and the melt rate of the nougat. The process begins with the sourcing of raw ingredients, including hazelnuts, sugar, cocoa powder, palm oil, skim milk powder, and vanillin. These ingredients are delivered to Nutella factories in massive quantities, requiring large-scale handling infrastructure. Hazelnuts, one of the key components of Nutella, are often sourced from Turkey and Italy, two of the largest hazelnut producers in the world. Upon arrival at the factory, hazelnuts are stored in enormous silos or temperature-controlled storage rooms to maintain their freshness. The silos are made of food-grade stainless steel and designed to protect the nuts from humidity and contamination, while allowing for precise dispensing into the production line. The first step in processing the hazelnuts is cleaning. Hazelnuts arrive in bulk shipments, often mixed with debris such as shells, stems, and dirt. To address this, the factory uses a series of cleaning systems that include vibrating screens, air classifiers, and magnetic separators. The vibrating screens shake the nuts to separate them from larger debris, while the air classifiers blow away lightweight impurities like husks and dust. Magnetic separators are also used to detect and remove any metallic particles that might have entered the shipment during harvesting or transport. Once cleaned, the hazelnuts undergo visual inspection using high-speed optical sorting machines equipped with cameras and sensors. These machines identify and remove any defective hazelnuts, such as those with discoloration, cracks, or signs of mold. After cleaning, the hazelnuts move to the roasting stage. Roasting is a crucial step in developing the rich, nutty flavor that characterizes Nutella. In the factory, this is achieved using massive industrial roasting ovens. These ovens are designed with rotating drums or conveyor belts to ensure even roasting. The temperature is carefully controlled, typically ranging between 280 and 320 degrees Fahrenheit, depending on the size and moisture content of the hazelnuts. Sensors monitor the temperature and time to ensure consistency, as over-roasting can lead to bitterness, while under-roasting can result in a lack of flavor. The entire roasting process is automated, and the equipment is designed for continuous operation to handle the high volume of hazelnuts required for production. Once roasted, the hazelnuts are transferred to grinding machines. These machines are equipped with heavy-duty stainless steel blades and rollers that crush the nuts into a fine paste. The grinding process occurs in multiple stages, with each stage further reducing the particle size of the hazelnut paste. In the initial stage, the nuts are coarsely ground into a chunky paste. In the subsequent stages, the paste is refined into a smooth consistency, with particle sizes measuring less than 30 microns. This ultra-fine grinding is essential for achieving Nutella's creamy texture. The equipment used in this process, such as colloid mills and ball mills, is highly specialized and designed to operate under high pressure and at precise speeds. The resulting hazelnut paste is collected in large stainless steel tanks, where it is stored at a controlled temperature to preserve its flavor and consistency. While the hazelnut paste is being prepared, the other ingredients are processed in parallel. Sugar, which provides sweetness to Nutella, is delivered to the factory in bulk containers or tankers. Upon arrival, the sugar is unloaded into silos, equipped with pneumatic conveying systems. These systems use air pressure to transport the sugar from the silos to the milling area, where it is ground into a fine powder. Industrial sugar mills are used for this purpose, and the grinding process ensures that the sugar particles are small enough to dissolve uniformly in the mixture. The factory also incorporates sieving systems to filter out any impurities or oversized sugar particles before they proceed to the blending stage. Cocoa powder, another key ingredient, undergoes a similar process. The cocoa powder is stored in sealed silos to protect it from moisture and contamination. Before being added to the Nutella mixture, the cocoa powder is sifted through vibrating screens to break up clumps and ensure a fine, even consistency. This step is crucial for achieving the smooth texture of the final product, as any clumps could create inconsistencies during blending. Palm oil, which gives Nutella its creamy consistency and prevents separation, is stored in large, temperature-controlled tanks. These tanks are equipped with heating elements to keep the oil in a liquid state, as palm oil tends to solidify at room temperature. The oil is pumped through insulated pipes to the mixing area, where it is carefully measured and added to the blend. The precise control of temperature and flow rate is essential to ensure that the oil integrates smoothly with the other ingredients. Skim milk powder, which adds a subtle dairy flavor and contributes to the creamy texture of Nutella, is stored in sealed containers or silos to prevent exposure to air and moisture. Before being used, the milk powder is sifted and screened to remove any lumps. Factories use advanced pneumatic conveying systems to transport the milk powder from the storage silos to the mixing area, ensuring that the ingredient is handled efficiently and hygienically. The blending process is the heart of Nutella's production, where all the prepared ingredients come together to form the final product. The blending tanks used in Nutella factories are massive, often with capacities of several thousand gallons. These tanks are equipped with high-speed agitators and temperature control systems. The hazelnut paste, sugar powder, cocoa powder, skim milk powder, palm oil, and vanillin are added to the tank in precise proportions, which are controlled by computerized dosing systems. These systems are programmed to weigh and dispense each ingredient accurately, ensuring consistency across batches. During blending, the mixture is heated slightly to help the ingredients combine more effectively. The temperature is carefully monitored, as excessive heat could alter the flavor and texture of the product. The blending tanks are designed to ensure even mixing, with agitators that create a vortex to incorporate all the ingredients thoroughly. The result is a homogeneous mixture with a smooth, creamy consistency. Once the blending process is complete, the mixture undergoes a refining stage. Refining is a critical step that ensures the final product is free of any graininess. The refining process takes place in multi-stage roller mills, which are equipped with heavy-duty steel rollers. These rollers apply immense pressure to the mixture, reducing the particle size of any remaining solids to less than 20 microns. This process not only enhances the texture of Nutella, but also improves its spreadability. The roller mills are fitted with precision sensors that monitor the pressure and temperature during refining, ensuring optimal performance. After refining, the mixture is transferred to the conching stage. Conching is a process borrowed from chocolate manufacturing and involves agitating the mixture in large, heated tanks for several hours. This process helps to further smooth the texture and enhance the flavor of the spread by allowing volatile compounds to evaporate and by evenly distributing the fats and solids. The conching tanks are equipped with paddles or rollers that knead the mixture continuously. The temperature and duration of conching are carefully controlled, as over-conching could negatively affect the spread's consistency. The finished Nutella is then pumped into holding tanks, where it is kept at a controlled temperature until it is ready for packaging. These tanks are equipped with agitators to prevent separation and maintain the spread's uniformity. Before the Nutella is packaged, it undergoes a final round of quality control. Samples from each batch are tested for flavor, texture, color, and viscosity. The factory uses advanced laboratory equipment such as viscometers and spectrophotometers to ensure that the product meets the company's stringent standards. Any deviations from the desired specifications are identified and corrected before the product proceeds to the packaging stage. Packaging is the final step in Nutella's production process, and it is carried out with the same level of precision and efficiency as the earlier stages. The spread is pumped from the holding tanks into automated filling machines, which dispense precise amounts of Nutella into jars. The filling machines are equipped with high-speed nozzles that can fill hundreds of jars per minute. Each jar is made from food-grade plastic or glass and arrives at the factory pre-sterilized to ensure hygiene. The jars are sealed with tamper-proof lids, which are applied and tightened using automated capping machines. Once the jars are sealed, they are conveyed to labeling stations, where Nutella's iconic branding is applied. The labels include important information such as the lot number, production date, and expiration date, which are printed using high-speed inkjet or laser printers. After labeling, the jars are inspected by vision systems that check for defects such as misaligned labels or damaged seals. Any defective jars are automatically removed from the production line. The jars are then packed into cardboard cartons using robotic packing systems. These systems are programmed to arrange the jars in specific configurations to maximize space and protect the jars during transportation. The cartons are sealed and stacked onto pallets using robotic palletizers. The pallets are then wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. The entire packaging process is designed for high efficiency, with minimal manual intervention and maximum output. Throughout the factory, automation plays a key role in maintaining efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems are used to monitor and control every aspect of the production process. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. The factory is also equipped with advanced robotics and machinery that ensure smooth operation, from ingredient handling to final packaging. Hygiene and safety are top priorities in Nutella factories. Production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Air filtration systems maintain a clean environment by preventing airborne contaminants from entering critical zones. Employees follow strict hygiene protocols, including wearing protective clothing and washing their hands regularly. The factory is regularly inspected to ensure compliance with international food safety standards, guaranteeing that every jar of Nutella is safe for consumption. This intricate, highly automated process ensures that Nutella is consistently smooth, flavorful, and delicious, meeting the high expectations of its millions of fans worldwide. Every step, from the handling of raw ingredients to the final packaging, is a testament to the engineering and precision that go into creating this beloved spread. The result is a product that continues to delight consumers, one jar at a time. Peanut butter, a staple spread beloved worldwide for its creamy or crunchy texture, requires a sophisticated and highly organized manufacturing process to meet the demand for consistent quality and flavor. Behind every jar of peanut butter is an intricate factory process that starts with the raw peanuts and ends with precisely packaged jars ready for distribution. Let's take an in-depth look at the factory production process, exploring the machines, systems, and engineering techniques that make it all possible. The process begins with the sourcing of raw peanuts. These peanuts are typically grown in countries like the United States, China, India, and Argentina, which are among the largest producers of peanuts globally. Peanuts are harvested in vast quantities, cleaned and dried at their source before being shipped to peanut butter manufacturing facilities. Factories require a consistent supply of high-quality peanuts, and to ensure that the raw peanuts are often tested upon arrival for size, moisture content, and overall quality. This ensures only the best peanuts are used for processing. Upon arrival at the factory, peanuts are stored in massive silos or bins designed specifically for food products. These silos are constructed from food-grade stainless steel or coated steel to prevent contamination and ensure proper hygiene. Inside the silos, the peanuts are protected from moisture, pests, and temperature fluctuations. These storage systems are equipped with conveyor systems that efficiently transfer peanuts from the silos to the initial cleaning and processing stages. The first step in processing peanuts is cleaning. Even though peanuts are partially cleaned at their source, factories implement a rigorous cleaning process to ensure no foreign materials or impurities remain. Vibrating screens are used to remove debris such as dirt, stones, and small sticks. Air classifiers blow air through the peanuts to remove lighter debris such as peanut skins or husks. Magnets are also employed to extract any metallic impurities. Optical sorting machines equipped with cameras and sensors scan each peanut as it moves along a conveyor belt, automatically removing any defective peanuts, including those with discoloration, mold, or deformities. After the cleaning process, the peanuts proceed to the roasting stage. Roasting is a critical step in peanut butter production, as it develops the rich, nutty flavor that defines the final product. Factories use industrial roasting ovens to roast the peanuts at controlled temperatures. These ovens come in two main types: batch roasters and continuous roasters. Batch roasters are used for smaller production lines, while continuous roasters, which use conveyor belts to move peanuts through a heated chamber, are used for larger scale operations. The temperature in these roasters typically ranges from 300 to 350 degrees Fahrenheit. The roasting process is closely monitored with temperature sensors and automated control systems to ensure the peanuts are roasted evenly. If some peanuts are over-roasted, they can turn bitter, while under-roasted peanuts may lack flavor. The level of roasting can also be adjusted depending on whether the final peanut butter will have a mild or more robust taste. Once roasted, the peanuts are cooled to stop the cooking process. Cooling is achieved by passing the roasted peanuts through chambers with powerful fans or cool air blowers. This step is crucial because it prevents the peanuts from continuing to cook, which could lead to inconsistencies in flavor. Some factories also use a water spray system to rapidly cool the peanuts, though this is less common as it can add moisture to the product. The cooling systems are designed to operate continuously to keep pace with the output of the roasting ovens. With the peanuts roasted and cooled, the next step is to remove their skins and separate the kernels. Skin removal is done using blanching machines. These machines have rotating drums or abrasive rollers that rub the peanuts, causing the thin outer skin to flake off. Some systems use steam blanching, where the peanuts are exposed to high-pressure steam to loosen the skins before mechanical removal. After blanching, the peanuts pass through air classifiers that blow away the loose skins, leaving behind clean peanut kernels. Factories also use gravity separators to sort peanuts by size and density, ensuring that only uniform peanuts proceed to the grinding stage. Before grinding, the peanuts are inspected again for quality. This is done using high-speed optical sorters that ensure any remaining defective peanuts are removed. Factories often have automated weighing and proportioning systems at this stage to determine the exact amount of peanuts needed for each batch. This level of precision is crucial for maintaining consistency in the flavor and texture of the peanut butter. The grinding process is the heart of peanut butter production. The roasted peanuts are fed into industrial grinders, where they are crushed into a fine paste. This process happens in multiple stages, beginning with coarse grinding and followed by finer grinding. The equipment used for this includes hammer mills and roller mills, which are specifically designed to reduce the peanuts into small, uniform particles. In many factories, the particle size is reduced to less than 20 microns, which is smaller than the diameter of a human hair. Achieving such a fine consistency is essential for the creamy texture that many consumers expect from peanut butter. For crunchy peanut butter, the process is slightly different. In these cases, a portion of the peanuts is coarsely ground and set aside before the final blending stage. These larger peanut pieces are later mixed into the smooth paste to create the characteristic crunchy texture. To prevent the peanut butter from separating, stabilizers such as hydrogenated vegetable oils or palm oil are added during the grinding process. These oils help bind the natural peanut oils to the solid peanut particles, ensuring a smooth and stable product that doesn't separate in the jar. Salt and sugar are also added at this stage to enhance the flavor of the peanut butter. Factories use precision dosing systems to measure and add these ingredients in exact proportions, ensuring every batch has the same taste. After grinding, the peanut butter is sent through a mixing stage, where it is further blended in large stainless steel tanks equipped with high-speed agitators. This stage ensures that the stabilizers, salt, and sugar are evenly distributed throughout the peanut butter. These tanks are often heated slightly to keep the peanut butter at the right consistency for mixing. The temperature is carefully controlled, as overheating can alter the flavor or texture of the peanut butter. Once the mixing is complete, the peanut butter undergoes quality control checks. Samples from each batch are tested in an on-site laboratory for flavor, texture, and consistency. Advanced instruments, such as viscometers, are used to measure the viscosity of the peanut butter, ensuring it meets the desired standards. Factories also use particle size analyzers to confirm that the peanut butter's texture is smooth and uniform. These quality checks are critical, as even slight variations can impact the final product's appeal to consumers. The final step in the manufacturing process is packaging. The peanut butter is pumped from the mixing tanks to filling machines, where it is dispensed into jars. These filling machines are capable of handling thousands of jars per hour, ensuring high efficiency. The jars, typically made of food-grade plastic or glass, arrive at the factory pre-cleaned and are sterilized again before filling. The filling nozzles are designed to dispense precise amounts of peanut butter into each jar, ensuring uniform weight and volume. Once the jars are filled, they move to the capping machines, where tamper-proof lids are applied and tightened. After capping, the jars are conveyed to labeling machines, which apply the brand's signature labels, along with lot numbers and expiration dates for traceability. Vision systems inspect each jar to ensure that the labels are correctly applied and that there are no defects in the seals or packaging. The jars are then packed into cardboard boxes using robotic packing systems. These robots are programmed to arrange the jars in specific configurations to optimize space and protect the jars during transportation. The boxes are sealed and stacked onto pallets using automated palletizing systems. Finally, the pallets are wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. Throughout the entire production process, automation plays a vital role in maintaining efficiency and consistency. Factories are equipped with programmable logic controllers, PLCs, and supervisory control and data acquisition, SCADA systems, that monitor and control every aspect of production. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. Robotic systems handle many tasks, from sorting and cleaning peanuts to packaging the final product, reducing the need for manual labor and ensuring precision. Hygiene and safety are also top priorities in peanut butter factories. The production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Positive air pressure systems prevent airborne contaminants from entering critical zones, while strict hygiene protocols ensure that employees maintain cleanliness throughout the production process. The entire facility is regularly inspected to comply with international food safety standards, ensuring that every jar of peanut butter is safe for consumption. Peanut butter production is a complex and highly technical process that relies on advanced machinery, precise engineering, and rigorous quality control. From the cleaning and roasting of peanuts to the grinding, mixing, and packaging of the final product, every step is designed to create a spread that is smooth, flavorful, and consistent. Factories operate with remarkable efficiency, producing thousands of jars per day to meet the global demand for this versatile and beloved product. Strawberry jam production is a fascinating and highly engineered process that combines precision machinery with time-tested techniques to create a smooth, fruity spread. At the core of this process are high-quality strawberries, sugar, pectin, and citric acid, all carefully handled and processed to achieve the perfect consistency and flavor. Inside a modern jam factory, every step is optimized for efficiency, consistency, and food safety. The process begins with the selection and delivery of fresh or frozen strawberries. Factories typically source strawberries from local farms or large-scale suppliers. Frozen strawberries are often preferred for large-scale production because they are preserved at peak ripeness, ensuring consistent flavor year-round. The strawberries arrive in bulk containers and are stored in cold rooms or freezers to maintain their quality until processing begins. Before entering the production line, the fruit undergoes a thorough cleaning process. This includes washing the strawberries in large tanks filled with filtered water, where gentle agitation removes dirt, debris, and any residual pesticides. Once cleaned, the strawberries pass through optical sorting machines. These machines use cameras and sensors to identify and remove defective or discolored fruit. Advanced systems can even detect minute imperfections, ensuring that only the highest quality strawberries make it into the jam. After sorting, the strawberries are sent to cutting or mashing machines, depending on the desired jam texture. For chunkier jams, strawberries are coarsely chopped, while for smooth spreads, they are mashed or pureed into a uniform consistency. The fruit then enters large stainless steel cooking kettles or continuous cooking systems. In these vessels, the strawberries are combined with sugar, which not only sweetens the jam, but also acts as a natural preservative. The sugar is added using automated dosing systems that measure precise quantities to ensure consistent flavor. Pectin, a natural thickening agent derived from fruit, is added to help the jam set. Citric acid is also incorporated to balance the sweetness and enhance the fruit's natural flavor. The mixture is slowly heated, with temperatures reaching up to 220 degrees Fahrenheit to activate the pectin and achieve the ideal gel-like consistency. During cooking, the jam undergoes constant agitation to prevent scorching and ensure even heating. Steam-jacketed kettles or vacuum cookers are often used as they allow for rapid and uniform heating. Modern vacuum systems are particularly advantageous because they enable cooking at lower temperatures, preserving the fresh flavor and bright color of the strawberries. Throughout the cooking process, sensors monitor the temperature, pH levels, and viscosity of the jam, ensuring that the final product meets strict quality standards. Once the jam reaches the desired consistency, it is pumped through a series of filters to remove any seeds or large pieces if a smoother texture is desired. The finished jam is then transferred to filling machines. These machines dispense precise amounts of jam into sterilized glass jars or plastic containers. The jars are immediately sealed with tamper-proof lids to maintain freshness and prevent contamination. After sealing, the jars are passed through pasteurization tunnels, where they are briefly heated to destroy any remaining microorganisms. Finally, the jars are labeled, inspected, and packed into cartons using robotic packaging systems. The entire process is highly automated, ensuring efficiency and consistent quality, from the arrival of fresh strawberries to the delivery of jars to store shelves. This seamless blend of traditional cooking techniques and advanced technology ensures that every jar of strawberry jam is rich in flavor, perfectly textured, and safe for consumers to enjoy. In a modern Oreo manufacturing facility, key dry ingredients are delivered in bulk, often by rail cars or food-grade trucks, and are pneumatically conveyed into large storage silos made of stainless steel or epoxy-lined carbon steel. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, they are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold, and they won't disperse evenly. Too hot, and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey: shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line: forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small, motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of 2 primary components: a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase, baking. Meanwhile, the excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient, capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from overprocessing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, the conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts, equipped with vision systems, scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds. Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronized parts of the process: sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual lane conveyors that separate and feed cookies into two different orientations: bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, a rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single-serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis, and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. Pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal. Hershey's chocolate production begins with the arrival of raw cocoa beans at its manufacturing plants, most notably in Hershey, Pennsylvania, where some of the largest scale chocolate operations in North America take place. These beans are imported from cocoa-producing regions around the equator, including West Africa and parts of Central and South America. Upon arrival, the beans are offloaded into receiving silos and moved into the first processing step: cleaning. Powerful vibrating screens, aspirators, and magnetic separators remove debris, stones, twigs, dust, and any metallic fragments that may have entered the shipment during transit. Following cleaning, the cocoa beans are fed into Hershey's proprietary roasting system. The roasting process is designed not just to sterilize the beans, but to precisely control flavor development. The machines are capable of adjusting roast temperature, humidity, and dwell time based on the origin, size, and moisture content of each batch. Beans are typically roasted at temperatures ranging from 120 to 160 degrees Celsius. This is where the characteristic chocolate aroma begins to develop, as volatile compounds are released and the Maillard reaction activates, producing hundreds of unique flavor notes that define Hershey's mild, sweet chocolate style. After roasting, the beans are cooled and moved to the winnowing section, where they are cracked open and the outer shells are separated from the valuable inner nibs. Winnowing is accomplished using a combination of mechanical cracking and airflow separation. The shells, now removed, are often collected and repurposed as agricultural mulch or biomass fuel. The nibs, the true essence of chocolate, contain both cocoa butter and cocoa solids and are now ready for the next phase: grinding. The nibs are fed into high-capacity industrial grinding mills, where intense mechanical shear forces break down the cellular structure and release the natural cocoa butter, forming a dense, fluid paste known as chocolate liquor. Despite its name, chocolate liquor contains no alcohol. This liquor is a pure, unsweetened, dark brown substance composed entirely of finely ground cocoa particles suspended in cocoa butter. From here, the liquor may go into temporary holding tanks or be immediately sent to blending tanks, depending on product demand. To make Hershey's classic milk chocolate, the chocolate liquor is blended with sugar, milk derivatives, cocoa butter, and small amounts of flavoring agents and emulsifiers. What makes Hershey's process unique is its use of fresh milk, originally pioneered by Milton Hershey himself, which is condensed and cooked on site. This milk is blended with sugar and chocolate liquor to form a slurry, which is then dried into what's known as milk crumb. The milk crumb is one of the keys to Hershey's signature, tangy, almost caramelized chocolate flavor. Unlike many European chocolate makers who use dry milk powders, Hershey's milk crumb production adds distinctive cooked dairy notes that have become synonymous with the brand's taste. The crumb mixture is then blended with additional chocolate liquor and cocoa butter in massive mixers to create a semi-fluid chocolate paste. This paste now contains all of the major components of Hershey's chocolate: milk solids, sugar, cocoa mass, and cocoa butter. However, it still needs to be refined to achieve the ultra-smooth texture that consumers expect. This refinement is achieved using a 5-roll mill, a piece of precision equipment where the chocolate paste is passed through a series of steel rollers that reduce particle size down to around 15 to 20 microns, small enough that the human tongue can no longer detect individual sugar or cocoa particles. Following refining, the chocolate mixture is fed into conchis, large horizontal vessels fitted with heavy-duty rotating arms. Conching is both a mechanical and thermal process in which chocolate is kneaded and aerated for several hours at controlled temperatures. During this stage, volatile acids are evaporated, off flavors are reduced, and cocoa solids become fully coated in cocoa butter, resulting in a more uniform flavor and mouthfeel. Hershey's conching times and temperatures are tightly guarded trade secrets, but generally range between 3 to 12 hours, depending on the chocolate type. Once conching is complete, emulsifiers like soy lecithin or PGPR may be added to improve flow characteristics and ensure the chocolate performs consistently during molding and enrobing. The now finished chocolate is transferred into tempering machines, where it is carefully cooled and reheated to stabilize the crystalline structure of the cocoa butter. Proper tempering is crucial to ensure the finished chocolate will have a glossy appearance, a sharp snap when broken, and resistance to fat bloom. Tempered chocolate is then routed to forming lines. For products like Hershey's milk chocolate bars or Hershey's Kisses, high-speed molding machines deposit the liquid chocolate into custom molds. These molds are vibrated to eliminate air bubbles and achieve uniform density before passing through long cooling tunnels. As the chocolate cools and solidifies, it contracts slightly and is released cleanly from the molds onto conveyors, ready for wrapping. Each chocolate piece is visually inspected, sometimes using high-speed cameras and vision systems, to ensure correct shape and fill. Hershey's Kisses, for example, go through dedicated foil wrapping machines that not only wrap each piece in branded foil, but also insert the iconic paper plume. Bars are fed into flow wrappers that apply sealed plastic or foil film, printed with lot numbers and expiration dates for traceability. From there, wrapped products are packed into cartons, sealed, labeled, and automatically palletized. Finished pallets are stored in climate-controlled warehouses maintained at stable temperatures and humidity to preserve texture, flavor, and appearance. Before any product is shipped out, samples from each production batch are tested in Hershey's quality control labs. There, technicians measure viscosity, particle size, pH, and fat content, and perform sensory evaluations to confirm that every batch meets the company's rigid standards for flavor and mouthfeel. Snickers, one of the most iconic candy bars in the world, is produced through a multi-stage industrial process that combines confectionery precision, mechanical engineering, and high-speed automation to create its distinctive layers of nougat, caramel, peanuts, and chocolate. Every bar must deliver the exact same ratio of texture and flavor, whether it's made in a facility in the United States, Europe, or Asia. With millions of bars produced daily, the manufacturing of Snickers is a tightly controlled operation with specific systems dedicated to each layer of the bar, all integrated into a seamless production line that ensures uniformity, food safety, and efficiency. From raw ingredient handling to final packaging, the Snickers factory operates with synchronized precision. Production begins with the preparation of the nougat layer, which forms the foundational base of every Snickers bar. The nougat used in Snickers is a whipped, chewy confection made from a combination of sugar, corn syrup, egg whites, milk powder, cocoa, and a small amount of salt. These ingredients are first loaded into industrial mixing vessels where they are cooked and then aerated. The sugar and corn syrup are heated together in a jacketed kettle until they reach a temperature between 115 degrees Celsius and 125 degrees Celsius. This heating process is tightly controlled through automated sensors that ensure consistent viscosity and prevent burning or crystallization. Once the syrup mixture reaches the desired temperature, it is transferred into a high-capacity continuous mixer, where egg whites and milk powder are added. Compressed air or nitrogen gas is also injected to whip the mixture into a soft, foamy texture. This aeration step is critical. It gives the nougat its characteristic lightness and chewiness. The temperature, gas pressure, and mixing speed are all precisely monitored by programmable logic controllers, which adjust the input in real time to maintain consistent product density and texture. The aerated nougat is then deposited as a thick slab onto a moving conveyor belt. This belt passes through a cooling tunnel that gradually reduces the temperature of the nougat slab to stabilize its structure. The cooling tunnel is divided into zones, each maintained at a different temperature to prevent rapid contraction, which could cause cracking or uneven density. Once cooled, the nougat slab is cut longitudinally into ribbons, the exact width of a Snickers bar, and then cross-cut into bar-sized sections using high-speed guillotine knives. These knives are synchronized with the conveyor's motion to ensure clean, accurate cuts without deforming the soft nougat. Next comes the caramel layer. The caramel used in Snickers is thick and elastic, designed to stretch but not melt under room temperature. It is made from a cooked blend of glucose syrup, sugar, milk solids, butterfat, and a carefully calibrated emulsifier. The cooking process begins in a steam-jacketed cooker, where the ingredients are brought up to approximately 118 degrees Celsius. The precise cooking temperature ensures the right balance between chewiness and flow. Overcooked caramel would become brittle, while undercooked caramel could seep through the nougat or ooze during packaging. Once cooked, the caramel is pumped into a depositor system that lays a continuous sheet of caramel over the cooled nougat ribbons. This depositor uses pressurized nozzles that spread the caramel evenly across the top surface of the nougat. The caramel is still warm and pliable at this point, allowing it to form a tight bond with the underlying layer. As the conveyor continues to move, the nougat and caramel combination enters another cooling tunnel where the caramel layer is firm to a stable consistency. Here again, the temperature gradient is critical. The cooling must be fast enough to stop flow, but slow enough to avoid separating from the nougat base. After the caramel is stabilized, whole roasted peanuts are applied. Snickers uses high-grade peanuts that are dry roasted on-site or sourced from dedicated peanut processors. These peanuts are first cleaned, sorted, and passed through color and size grading machines. Roasting is carried out in rotary drum roasters, where temperatures are maintained around 160 degrees Celsius. After roasting, peanuts are cooled rapidly using ambient or forced chilled air to stop the cooking process and retain crunch. The cooled peanuts are then sprinkled over the still sticky caramel layer using a controlled vibratory feeder. These feeders dispense peanuts in an even distribution, and excess nuts are collected and recirculated to avoid waste. Once applied, the peanut caramel nougat stack moves through a compression station where soft rollers press the peanuts gently into the caramel to ensure adhesion. This step is essential to prevent peanuts from falling off during enrobing and packaging. The multi-layer slab is then cut again, first lengthwise into individual bar width strips, then crosswise into single units. High-speed ultrasonic knives are often used in this phase to make clean cuts through the sticky peanut caramel mass without dragging or deforming the shape of the bar. These knives vibrate at ultrasonic frequencies, reducing friction and keeping each cut smooth and precise. As with earlier cutting stages, sensors track bar dimensions, and any piece that falls outside specified tolerances is rejected automatically. Now, the cut bars are conveyed into the enrobing chamber, where they are coated with milk chocolate. The chocolate used in Snickers is a proprietary milk chocolate blend containing cocoa solids, cocoa butter, sugar, milk powder, and emulsifiers. This chocolate is kept in tempering tanks where it is heated and cooled in a controlled cycle to form stable cocoa butter crystals. Proper tempering is crucial for ensuring that the chocolate coating is glossy, has the right snap, and doesn't develop fat bloom over time. Inside the enrober, each bar passes over a fine mesh conveyor that dips the underside of the bar in chocolate. A curtain of tempered chocolate then flows over the top of each bar, fully enrobing it. Excess chocolate is removed by controlled air jets or vibrating mechanisms, which ensure a consistent coating thickness without pooling or streaking. As the chocolate sets, decorative ribbons or textures may be applied to the top surface using nozzles or air patterns. After enrobing, the bars enter the final cooling tunnel. This tunnel is typically 20 to 30 meters long and divided into multiple zones, with temperatures gradually decreasing from around 15 degrees Celsius to 5 degrees Celsius. The goal here is to allow the chocolate to crystallize into a firm, uniform shell without cracks or surface defects. Conveyor speed and cooling tunnel temperature are constantly adjusted to account for changes in factory humidity or chocolate flow rate. Once the bars exit the cooling tunnel, they move to the packaging area. Here, vision systems inspect the bars for defects, such as incomplete coating, misshapen forms, or incorrect size, and reject any units that don't meet quality standards. Accepted bars move into a high-speed flow wrapping machine. This machine dispenses printed plastic film from large rolls, forms it into a sleeve around each bar, seals the ends and back, and prints lot numbers, expiration dates, and traceability codes onto the packaging. Bars are grouped and packed into cartons automatically, then palletized using robotic arms or automatic stackers. Each pallet is labeled with its production date, factory ID, and batch number, and stored in a temperature-controlled warehouse. Finished Snickers bars are shipped daily to retailers, wholesalers, and export hubs with real-time tracking through the company's logistics and ERP systems. This ensures traceability from raw ingredient to retail shelf and allows for rapid recall or investigation if any quality issue arises in the field. Snickers production is supported by continuous quality assurance throughout every phase. From incoming raw ingredients to the final product, quality technicians perform random sampling and laboratory testing for moisture content, peanut roast quality, chocolate temper index, caramel viscosity, and microbial counts. Every component, nougat, caramel, chocolate, peanuts, is monitored to within narrow tolerances. If even a single component batch shows deviation, it can be traced, flagged, and excluded from the production cycle. In addition to quality, food safety and hygiene are rigorously maintained. All machinery is subject to clean-in-place protocols, and workers adhere to strict sanitation and allergen handling rules. Due to the presence of peanuts, dedicated production zones and air handling systems are used to prevent cross-contamination with other product lines in multi-product factories. The Snickers production process is also increasingly supported by digital technology. Smart sensors, machine learning models, and real-time analytics are used to monitor equipment performance, detect subtle variances, and suggest preventative maintenance. Digital twins of the production line can simulate different production scenarios, like ingredient substitutions or temperature fluctuations, to predict impacts before they occur in the real world. This data-driven approach allows Mars, Inc., the manufacturer of Snickers, to continuously refine and optimize its production across multiple global sites. Twix is a beloved chocolate bar recognized globally for its iconic combination of crisp biscuit, chewy caramel, and smooth milk chocolate. Its appeal lies in the precise layering and the uniformity with which each bar delivers the same balance of texture and flavor. Behind its simple appearance is a highly engineered manufacturing process that seamlessly integrates baking, confectionery science, and automated packaging on a vast industrial scale. Producing millions of Twix bars daily in factories around the world requires meticulous coordination across every step of production, from dough mixing to chocolate enrobing, all operating under strict food safety protocols and quality control systems. The following in-depth look walks through the entire process, detailing how Twix is made in a modern factory environment, step by step, with over 1,600 words devoted to the subject. The process begins with the foundation of the Twix bar, the biscuit base. This shortbread-like component is central to the signature texture of Twix, light, crunchy, and buttery without being too sweet. The ingredients for the biscuit base include wheat flour, vegetable oil or shortening, sugar, salt, and leavening agents. These raw materials are delivered to the facility in bulk, typically stored in stainless steel silos or sealed containers to protect against moisture and contamination. The dry ingredients are conveyed into high-capacity horizontal mixers, where they are combined with fats and a small amount of water. These mixers are programmed to replicate the specific time, temperature, and mixing intensity needed to create the ideal dough consistency. Overmixing is carefully avoided to prevent gluten development, which would make the biscuit tough rather than tender and crisp. The dough is monitored for temperature, moisture content, and texture using inline sensors, ensuring consistency across every batch. Once mixed, the dough is transferred to a sheeting machine. This equipment rolls the dough into a uniform sheet of precise thickness, typically between 5 to 7 millimeters, depending on the specific product variant. The sheet passes through multiple sets of rollers to ensure evenness, then moves toward a rotary cutter that stamps out the biscuit fingers. Each finger is carefully spaced on a baking band to prevent sticking or deformation during baking. Excess dough, or webbing, is collected automatically, recycled, and fed back into the mixer for reuse, minimizing waste. The cut biscuits are conveyed into a tunnel oven, often more than 30 meters long, and divided into multiple temperature zones. The ovens are typically gas-fired and utilize forced convection to ensure even heat distribution. Baking profiles are carefully managed. The temperature starts lower to allow for expansion and rises toward the middle and end of the tunnel to set structure and achieve the golden brown exterior. The baking process typically lasts around 8 to 12 minutes. The final product emerges dry, crisp, and structurally sound to support the next layers of caramel and chocolate. After baking, the biscuits are cooled on a long spiral or tiered cooling conveyor. It is essential that they reach ambient temperature before caramel application, as residual heat could soften the caramel or cause bonding inconsistencies. Airflow systems within the cooling unit are calibrated to prevent moisture buildup, which could compromise the crispness of the biscuit layer. Next is the caramel layer, one of the most technically challenging aspects of the Twix manufacturing process. The caramel must be viscous enough to form a thick, even layer on the biscuit, yet firm enough to retain its shape during cutting, enrobing, and packaging. It must also stretch slightly when bitten into, without melting or breaking apart. The caramel is prepared in large, jacketed cooking kettles or continuous caramel cookers. The ingredients: glucose syrup, sugar, milk solids, fats, and sometimes salt and flavorings are heated to a controlled temperature around 118 to 120 degrees Celsius. Cooking caramel to the correct temperature is critical. Any deviation can result in too hard or too runny caramel. The factory's automated control systems monitor brix levels, temperature curves, and viscosity in real time. Adjustments are made instantly if readings deviate from the set parameters. Once cooked, the caramel is pumped into a depositor system. This system deposits a continuous ribbon of hot caramel directly onto the cooled biscuit fingers, which are now moving along a precision conveyor belt. Depositors can be adjusted to control caramel height and width, ensuring even coverage. The caramel must adhere firmly to the biscuit and cool rapidly to a semi-firm consistency to hold its shape through the subsequent chocolate enrobing process. The bars now enter a cooling tunnel for caramel setup. This tunnel is maintained at a lower ambient temperature and spans several meters to allow gradual cooling without thermal shock. As the caramel cools, it solidifies just enough to support chocolate coating without running or shifting. This balance is critical for appearance, structural integrity, and mouthfeel. Once the biscuit and caramel layers are firmly bonded, the bars proceed to the chocolate enrobing phase. This is where each Twix bar is fully coated in a layer of milk chocolate. The chocolate used is a proprietary blend formulated specifically for Mars, Inc., and it includes cocoa butter, milk powder, cocoa solids, sugar, and emulsifiers, such as soy lecithin, to ensure proper flow. The chocolate is first tempered, a process that involves heating, cooling, and reheating to encourage the formation of stable cocoa butter crystals. Proper tempering gives the final chocolate coating its shine, snap, and resistance to fat bloom. In large-scale operations, tempering is achieved using continuous tempering machines that monitor crystal formation, viscosity, and flow rate. The tempered chocolate is pumped into an enrober, which is essentially a tunnel where a curtain of chocolate flows from above and a shallow pool coats the bottom. The bars pass through this curtain and are submerged briefly in the bottom coating layer, ensuring all sides are covered. Air knives or vibrating plates remove excess chocolate, and decorative features, such as surface ripples, may be added by adjustable nozzle heads or vibration patterns. The chocolate-coated bars are immediately conveyed into another cooling tunnel, this one much longer and colder, designed to gradually bring the chocolate to a solid state without creating bloom or surface imperfections. The cooling tunnel maintains a strict temperature gradient, starting around 18 degrees Celsius and lowering to 10 degrees Celsius by the end, over a 5 to 10 minute period. As the bars exit the cooling tunnel, they are fully formed Twix bars, but they're not yet individually packaged. They move directly into the high-speed wrapping area. Each bar is aligned and spaced using puck systems or lane guides to ensure it enters the flow wrapping machine correctly. Here, rolls of branded film are fed into the wrapper, folded tightly around the bar, and sealed on all sides using heat and pressure. The film is pre-printed with logos, batch codes, nutritional data, and sometimes promotional graphics. Each wrapped bar is weighed and passed through metal detectors or X-ray scanners to ensure it meets food safety standards. Any bar outside of weight tolerance or showing contamination is automatically diverted. Accepted bars are grouped into multi-packs or display boxes using robotic pickers or diverters, then loaded into shipping cartons. The cartons are coded with tracking data and palletized using automatic palletizers. Each pallet is scanned into inventory and staged for shipping. Throughout the factory, Quality control technicians pull samples at regular intervals to test for key performance attributes: biscuit density, caramel thickness, chocolate adhesion, weight, sensory characteristics, and packaging integrity. The factory also operates under a HACCP framework, meaning each step of the process is mapped for potential hazards and monitored with critical control points. Twix manufacturing is highly dependent on repeatability, and thus, much of the factory's infrastructure is built around statistical process control and automation. PLCs communicate with sensors on every machine, feeding data to a centralized control room. This enables supervisors to watch live readouts of oven temperatures, caramel cooker output, chocolate temper readings, fill weights, and wrapper speed, all updated every second. Alarms and automatic corrections are built into the system, allowing for real-time adjustments without stopping production. Beyond process precision, Twix production lines are designed for flexibility. Factories can run product variations, including Twix miniatures, Twix ice cream bars, Twix cookies and cream, or seasonal additions like white chocolate or dark chocolate. Changeovers between product formats involve switching molds, adjusting depositor nozzles, changing film rolls, and flushing chocolate lines, all of which are guided by detailed standard operating procedures to avoid cross-contamination and ensure food safety. Once finished, Twix bars are shipped to distribution centers or directly to retailers. During shipping, temperature control remains important, particularly in warm climates where chocolate is susceptible to melting. Pallets may be moved using temperature-controlled trucks or packed with insulation to protect product integrity. Inventory is rotated on a first-in, first-out basis to ensure freshness and shelf life management. At the retail end, Twix must retain not only its visual appeal, but its textural signature. The snap of the biscuit, the chew of the caramel, and the smoothness of the chocolate are all the result of hundreds of synchronized steps and checks across a production system built for consistency at scale. From ingredient sourcing to the final shipping pallet, every detail is fine-tuned to preserve the brand's identity and ensure that each bite of Twix tastes exactly as expected: crisp, creamy, and perfectly layered. Chocolate begins its life not in the factory, but on the tropical cacao farms that line the equator. These farms are located in countries across West Africa, Central and South America, and Southeast Asia, with Ivory Coast and Ghana among the world's top producers. The climate in these regions, hot, humid, and with rich, well-draining soil, is essential for the cultivation of Theobroma cacao, the tree that produces cacao pods. Each pod contains 20 to 50 seeds, known as cacao beans, surrounded by a sweet, pulpy, white fruit. These beans are the raw foundation of all chocolate products. The cacao harvest is entirely manual. Farmers use machetes or curved knives attached to long poles to carefully cut ripe pods from the trees without damaging the branches. A single mature tree may produce between 20 and 30 pods per year, and since cacao does not ripen all at once, harvesting occurs continuously over several months. Once harvested, the pods are collected in piles and opened by hand using machetes. The beans, still coated in sticky white pulp, are scooped out and prepared for fermentation, the first transformative step in the chocolate-making process. Fermentation typically occurs on the farm or at centralized collection centers. Though it might sound like a simple resting period, fermentation is a critical and highly sensitive step that chemically alters the beans and begins to develop the flavor precursors of chocolate. Beans are placed in shallow, slatted wooden boxes or piled into heaps and covered with banana leaves. This environment encourages the growth of natural yeasts and bacteria that convert sugars in the pulp into alcohol and acids. As the temperature rises, often reaching 45 to 50 degrees Celsius, the bean's internal structure changes. Enzymes are activated, cell walls are broken down, and bitter polyphenols begin to transform into the complex flavor compounds that will later give chocolate its signature taste. Fermentation typically lasts 5 to 7 days, during which the beans are turned or mixed once or twice a day to ensure even microbial activity and oxygenation. This step is closely monitored, as under-fermentation leads to bland or vegetal flavors, while over-fermentation can introduce off notes like mold, vinegar, or excessive bitterness. Many large chocolate manufacturers, even though they don't ferment beans on site, have established quality programs with their cacao suppliers, training them in fermentation control, and even requiring on-site testing of pH and temperature during the process. Once fermentation is complete, the beans are spread out to dry. Drying can be done on large tarpaulins, bamboo mats, or raised wooden platforms under the sun. Industrial cacao processors often prefer sun drying, which can take 5 to 10 days, as it produces cleaner, more natural flavor profiles. During drying, the beans are turned regularly to ensure even moisture loss. The goal is to reduce the moisture content to around 6%, 7%, a safe level that prevents mold and microbial growth during storage and transport. At this point, the beans are still covered in their thin, brittle shells and have taken on a dark brown color, with their signature earthy, chocolatey aroma starting to develop. The beans are carefully bagged in burlap sacks, usually 60 to 65 kilograms per bag, and labeled with origin information including country, region, farm or co-op, and processing dates. These bags are then consolidated for export. Exporting cacao beans requires extreme care and logistics planning. Moisture, heat, and exposure to foreign odors can degrade the beans before they even reach the factory. To prevent spoilage, the sacks are loaded into dry, ventilated shipping containers, often lined with insulating material or desiccant packs to control humidity. During long overseas shipments, particularly by sea freight, the cargo is monitored using data loggers that track temperature and humidity. If the beans are exposed to extreme conditions, entire shipments can be rejected by the receiving chocolate manufacturer. When the beans arrive at the chocolate factory, usually located in Europe, North America, or Asia, they undergo a rigorous intake and inspection process. This is where industrial chocolate production truly begins. First, the bags are unloaded into a receiving area, where samples are drawn from each lot and taken to the quality control lab. Here, technicians measure moisture content, check for mold or insect damage, and grade the beans based on size, color, and cut tests. Cut tests involve slicing a sample of beans lengthwise and examining the cross-section. Properly fermented beans will have a uniform, slightly purplish interior with no signs of germination or off colors. Beans that meet the manufacturer's standards are then approved for processing. The sacks are emptied into large hoppers that feed the cleaning and pre-processing line. At this point, the factory begins to function much like a grain mill, sorting, cleaning, and prepping the raw material for transformation. The first stage is mechanical cleaning. The beans pass through vibrating screens and air jets that remove sticks, stones, dust, string, and other foreign materials. Magnetic separators remove any stray metal particles picked up during harvest or shipping. After cleaning, the beans are often sorted by size. This is an optional step, but many high-end chocolate makers insist on sorting to ensure that beans of uniform size are roasted together. Uneven roasting is a major risk if large and small beans are mixed, as the small beans may burn while the larger ones under-roast. Before roasting, the factory may also conduct a dehumidification step, particularly if the beans arrived slightly above target moisture. Large rotary dryers or low-temperature ovens are used to bring the beans into precise moisture range, often 5%, 6%, to prepare for optimal roast conditions. This is all monitored through programmable logic controllers that track time, temperature, airflow rate, and moisture loss in real time. With the cacao beans now thoroughly cleaned, dried to precise moisture levels, sorted by size, and passed through rigorous quality inspections, the chocolate production process enters one of its most transformative and delicate phases: roasting. This step marks the moment when raw agricultural product begins to develop the hallmark sensory properties of finished chocolate: aroma, depth, bitterness, sweetness, and complexity. Far from being a simple baking process, industrial chocolate roasting is a finely tuned science that must balance heat, time, air circulation, and even bean origin to unlock the flavor potential locked within the bean's cellular structure. The roasted profile of chocolate is not one size fits all. It varies greatly depending on the origin of the beans, the desired flavor profile of the final product, and the style of chocolate being produced, whether it's milk, dark, or even single origin specialty bars. As such, chocolate factories have roasting protocols tailored to each bean variety and product type. These protocols are logged as roast profiles, charts that map temperature over time, often broken into phases: drying, browning, and development. Each phase requires precise thermal input and airflow to extract the right flavors without burning or flattening the bean. Industrial chocolate factories use several types of roasters depending on scale and product goals. The most common are batch drum roasters and continuous roasters. Batch drum roasters, similar in design to coffee roasters but much larger, feature a rotating cylindrical drum made from stainless steel. Beans are loaded into the drum, which rotates over direct or indirect heat, with hot air circulated through the drum chamber. Temperature sensors embedded in the drum monitor the bean mass, ambient air, and exhaust temperatures simultaneously. Factory operators can adjust drum speed, airflow rate, and burner intensity through PLC-controlled interfaces to manage the roast curve. Roasting typically begins at a lower temperature, around 100 degrees Celsius, to drive off any remaining surface moisture. This is the drying phase and usually lasts for 5 to 10 minutes. The beans then enter the browning phase, where the Maillard reaction begins. This is the chemical process that causes amino acids and reducing sugars in the beans to recombine and form hundreds of flavor compounds: nutty, roasted, caramelized, and acidic notes that are essential for chocolate's complexity. This phase is carefully controlled, usually taking another 10 to 15 minutes, with bean temperatures rising to 120-140 degrees Celsius. The final stage of roasting is known as development, or the finishing phase. Here, the beans are brought to their final internal temperature, typically between 135 degrees Celsius and 150 degrees Celsius, depending on the desired flavor profile. This phase is brief, often just 2 to 5 minutes, but it's critically important. Too little development, and the flavor may be grassy or underwhelming. Too much, and the chocolate may taste burnt, acrid, or flat. Advanced factories use real-time infrared cameras and bean temperature probes to monitor this phase with incredible accuracy, sometimes recording temperatures at 1-second intervals. After roasting, the beans must be cooled quickly to halt the cooking process. This is usually achieved in a dedicated cooling drum or tray system, where ambient or chilled air is blown across the beans using high-speed fans. Cooling not only stops the roast, but it also firms up the bean shell and prevents steam buildup, which could cause condensation or spoilage during storage. At this point, the beans are dark brown, fragrant, and brittle, but they still contain their outer shells, a thin, papery husk that must be removed to access the valuable interior, the cacao nib. The next phase is known as winnowing. Winnowing is a mechanical process that cracks the beans open and separates the lightweight shells from the dense nibs using a combination of crushing and air classification. In a large-scale chocolate factory, beans are first passed through a pre-cracker or roll crusher, which breaks them into fragments of varying size. The cracked mixture is then fed into a winnowing chamber, often a series of vertical air columns or vibrating conveyor belts, where calibrated air jets or suction systems separate the heavier nibs from the lighter shells. The airflow is precisely tuned so that the nibs fall to the bottom collection bins while the husks are drawn upward into separate waste hoppers. The result is a batch of pure cacao nibs, dark, rich, and packed with flavor and cocoa solids. These nibs are now ready to be transformed into chocolate liquor, not an alcoholic beverage, but a thick, paste-like substance made from finely ground cacao nibs. This is where the chocolate truly begins to take shape. To produce liquor, the nibs are passed through industrial grinders known as pre-refiners or impact mills. These machines use either rotating steel blades or stone rollers to shear the nibs into smaller and smaller particles. As the nibs are ground, frictional heat causes the cocoa butter inside to melt. This transforms the mixture from a coarse, gritty powder into a flowing paste with a smooth, velvety texture. The grinding process typically reduces particle size to around 80 to 100 microns during this first stage. From here, the liquor is either held in heated tanks for further processing or sent directly to the next grinding phase, refining. Refining is the step where particle size is further reduced to achieve the smooth mouthfeel expected from high-quality chocolate. This is performed using 5-roll refiners or ball mills. 5-roll refiners consist of 5 horizontally stacked steel rollers, each rotating at a different speed. The chocolate liquor is fed into the gap between the rollers, which progressively shear the particles down to between 15 and 25 microns. At this size, individual cocoa and sugar particles are too small for the tongue to detect, giving chocolate its creamy texture. In factories producing sweetened chocolate, sugar is added during this refining phase. The sugar, already pre-milled to ensure consistent granule size, is blended with the chocolate liquor to form what's called a chocolate crumb. Depending on the recipe, milk powder, vanilla, lecithin, and other ingredients may also be added at this stage. These additions are carefully weighed and dosed using automated batching systems, which ensure that every batch conforms to a master formulation. After refining, the chocolate mass still feels dry and powdery. To turn it into a cohesive, pourable liquid with a smooth finish and stable flavor, it must undergo conching, a prolonged mixing and aeration process that can last anywhere from several hours to multiple days. Conching takes place in large heated vessels fitted with rotary arms or heavy granite rollers. The goal of conching is threefold: to develop flavor by oxidizing volatile acids, to smooth texture by distributing fat uniformly, and to improve viscosity by reducing moisture and undesirable compounds. The conching process is controlled in phases: dry conching, where the paste is crumbly and thick; plastic conching, where it softens and flows; and liquid conching, where the mass becomes fully fluid. Each conching profile is custom tailored to the specific chocolate type being produced. Milk chocolate, for instance, requires longer conching to balance milk solids and sugars, while high percentage dark chocolate may be conched shorter to retain more of its natural acidity and origin flavor. Throughout conching, temperature, shear force, and oxygen flow are all regulated. Some factories utilize closed-loop conches with nitrogen blanketing to reduce oxidation, while others incorporate vacuum systems to pull out undesirable volatile compounds. This stage is monitored using inline viscometers and gas sensors, ensuring consistent output from batch to batch. At this point in the process, the chocolate mixture has reached a smooth, glossy, and richly aromatic state. It flows as a thick liquid, its flavors matured and balanced from hours of careful mixing, grinding, and aeration. The next phase transforms that liquid mass into a finished, stable form suitable for packaging and distribution. This involves cooling and crystallizing the cocoa butter within the mixture in a very specific way. a stage that requires precision and control over time, temperature, and movement. The goal here is to encourage the formation of the right type of crystal structure in the cocoa butter. Cocoa butter can solidify into several different crystalline forms, but only one of them results in a final product that has a smooth surface, sharp snap, resistance to melting in the hand, and a stable shelf life. To achieve this, the entire mass must be carefully tempered. Tempering is carried out in machines built for continuous flow and temperature control. These tempering units begin by first heating the mixture slightly above the melting point of all crystal forms, typically around 45 degrees Celsius. This ensures that any existing crystal structures are completely melted away. The liquid is then cooled gradually, usually to somewhere between 26 degrees Celsius and 28 degrees Celsius, depending on the specific type being produced. During this cooling, movement is maintained through stirring blades and flow channels, allowing the desired type of stable crystal to begin forming. Once enough of these seeds have developed, the mixture is gently reheated to a precise finishing temperature, usually just under 32 degrees Celsius. This final temperature is critical. It allows the seeded crystals to remain while eliminating the unstable forms that would cause bloom or textural issues later on. The flow, agitation, and temperature must be maintained within a very tight range. Modern tempering equipment uses inline sensors and feedback control loops to monitor these values in real time, ensuring the product is correctly tempered before it moves into the next station. From here, the tempered liquid is conveyed to the molding lines. These are high-speed, fully automated systems designed to pour precise volumes into molds of various sizes and shapes. The molds themselves are preheated slightly to prevent premature setting and ensure even flow. As the mixture is deposited into each cavity, vibratory tables shake the molds to remove any trapped air bubbles and ensure a perfectly even distribution. Once filled and vibrated, the molds are sent through long cooling tunnels. These enclosed, refrigerated belt systems gradually reduce the temperature in controlled stages, allowing the internal structure to set without cracking or warping. The airflow, tunnel speed, and humidity are all precisely calibrated to avoid moisture condensation on the surface, which could lead to dull or sticky finishes. Once cooled and fully solidified, the bars or shapes are released from the molds using a combination of mechanical pushes and short bursts of air. The finished items are then transferred onto conveyors that lead to the inspection zone. Here, vision systems scan each piece for defects, looking for uneven surfaces, cracks, color inconsistency, or any signs of bloom. Imperfect units are automatically ejected from the line for recycling. In many operations, these rejected items are remelted and retempered to be used again in the next batch. From this point, the finished product moves toward wrapping and packaging. The type of packaging depends on the product format, whether individual bars, boxed assortments, filled shapes, or bulk items for further processing. For single bars, wrapping lines are designed to handle high volumes per minute. Each bar is conveyed through a wrapping machine that cuts, folds, and heat seals the wrapper with high-speed precision. These machines are synchronized with the flow of the production line to prevent jamming, tearing, or misalignment. Packaging materials include metallized films, waxed paper, biodegradable foils, or composite laminates. These materials are selected based on the storage requirements of the product, the region's environmental regulations, and the shelf life goals. Many manufacturers also include oxygen scavengers or modified atmosphere sealing to enhance freshness, especially for filled products. After wrapping, individual bars or pieces are grouped into larger cartons or boxes by pick-and-place robotics. These machines identify product orientation, pick them up using suction or mechanical fingers, and place them into retail boxes, display trays, or bulk cases. The outer cartons are sealed, labeled, and pass through final quality control scanners that confirm weight, barcode accuracy, and expiration coding. Palletizing comes next. Stacked and secured cartons are placed onto shipping pallets according to loading patterns that maximize space efficiency and minimize stress on the bottom layers. Pallets are shrink-wrapped using rotating arms or heat tunnels, and then labeled with shipping codes, batch numbers, and destination data. The entire production record for each batch is digitally logged in the factory's quality control database. This includes source information for the raw ingredients, roasting and grinding parameters, conching durations, tempering temperatures, molding timestamps, and final inspection results. Should any issue arise downstream in distribution or retail, the system allows full traceability back to the moment each unit was created. Finished pallets are moved to climate-controlled storage zones. These warehouse areas are kept at stable temperatures, generally between 16 degrees Celsius and 20 degrees Celsius, to prevent melting, blooming, or flavor degradation. Humidity is also controlled, often under 60%, to protect the product and packaging integrity. Some products are stored under specific lighting conditions to prevent discoloration, particularly white and milk varieties that are more sensitive to UV exposure. Finally, shipments are released according to production schedules aligned with distribution needs. Orders are grouped by destination region, retailer, or distributor and loaded into trucks, shipping containers, or cargo planes. Temperature data loggers may be placed inside shipments to confirm that climate conditions remain within acceptable limits throughout transport. Though the product has now left the facility, its connection to the factory process is never lost. Retail complaints, test results, or customer feedback can all be traced back to the specific day, shift, and equipment used. Manufacturers regularly run shelf life simulations, flavor degradation tests, and mechanical stress analyses on packaged goods to validate the effectiveness of the process long after the final product leaves the line. Every stage, from raw bean to packaged bar, is designed not just for efficiency, but for repeatability and control. Factories producing chocolate operate like laboratories with strict protocols, while still honoring the craft behind each ingredient's transformation. This combination of technical discipline and sensory artistry is what makes industrial chocolate manufacturing one of the most exacting and fascinating operations in the global food industry. Once the finished chocolate leaves the factory, perfectly tempered, molded, cooled, and sealed in its final packaging, the industrial process doesn't come to a halt. A crucial final phase still unfolds, one that ensures the product not only reaches shelves in perfect condition, but also maintains its quality and integrity through transportation, storage, retail display, and eventual consumption. This extended phase is managed through sophisticated logistics, environmental monitoring, supply chain coordination, and continuous quality assurance practices. While this may seem like the back end of production, it is deeply integrated into how chocolate is made and maintained on a global scale. Immediately after production, the packaged chocolate is transferred into climate-controlled storage areas within the factory's distribution wing. These areas are tightly regulated to prevent degradation. The ideal temperature for storing finished chocolate is generally between 16 degrees Celsius and 20 degrees Celsius, with humidity kept below 60%. Above this humidity threshold, there is risk of sugar bloom, a white, dusty coating that forms when moisture causes sugar to dissolve and then recrystallize on the surface. Below this range, especially in dry climates, static electricity and brittleness can become issues, particularly for filled or aerated varieties. Storage racks are arranged to allow airflow between pallets. Each pallet is tagged with a unique identifier and scanned into the warehouse management system. This allows the system to track not only where each batch is physically stored, but also how long it's been in inventory, where it needs to go next, and whether it's awaiting any last-minute quality hold releases. Before a batch can ship, a final set of post-production tests is sometimes performed on a sample group. These tests may include accelerated shelf life simulations, where chocolate is exposed to varying environmental conditions in climate chambers to determine how it performs over time. Texture analyzers may test for brittleness or softening, while gas chromatography may be used to check whether volatile flavor compounds remain stable. Once cleared, shipments are scheduled for distribution. Whether headed to a supermarket distribution center, a specialty retailer, or international export, the chocolate must be loaded into transport systems that preserve the exacting conditions it was stored under. This can involve refrigerated or climate-controlled trailers, especially for higher-end varieties or filled products that are more vulnerable to heat. During warmer seasons, some companies delay shipments until nightfall or equip their pallets with insulation wraps to preserve temperature during brief exposure windows. Transport vehicles are often equipped with onboard temperature loggers. These small, battery-powered devices record environmental conditions every few minutes and are reviewed upon delivery to confirm that there were no unacceptable spikes in heat or humidity. If the data shows a breach, the receiving party may reject the shipment, even if the exterior packaging appears untouched. This level of accountability ensures that the integrity of the product is never assumed, but always confirmed. At the retailer level, chocolate continues to face environmental risks. Supermarkets and convenience stores may place chocolate in non-refrigerated aisles where exposure to lighting, fluctuating temperatures, and air conditioning vents can impact quality. To mitigate this, factory teams sometimes conduct in-store audits, either directly or through contracted merchandising specialists. These audits include checks on product placement, shelf temperature, rotation practices, and visible quality. Manufacturers also perform pull tests, where random samples are purchased directly from stores and sent back to internal labs for analysis. This helps determine if the product maintains its texture, snap, and flavor after weeks or months in the distribution system. These real-world results are fed back into the production process, helping engineers refine shelf life goals, tweak packaging barrier specifications, or adjust emulsifier ratios for better thermal resilience. Despite this rigorous system, the industrial process isn't rigid. Many manufacturers now build flexibility into their operations to support seasonal releases, new flavor experiments, and evolving consumer preferences. This includes small batch production lines within large factories that can produce limited runs of new recipes without interrupting mass-scale output. Even with these small lines, all the same steps: roasting, refining, conching, tempering, molding, wrapping are followed precisely, but in more agile formats. The long arc of chocolate production, from tropical farm to factory and beyond, is a story of transformation, precision, and protection. Each stage is critical, from developing flavor precursors during fermentation, to unlocking complexity through roasting, to achieving that final, glossy finish through proper tempering and cooling. It's not just about creating a product, it's about preserving it, tracking it, testing it, and delivering it across continents in exactly the state it was intended.